Goal for this video is to start to understand the nature and the use of what's called the standard normal distribution. And by doing that, we can start to begin to look at questions that you might be able to see just in front of you there. Here. So let's say we have two students who do two different maths tests. Maybe they're at nearby schools and it's the same maths subject in senior, you know what I mean? And student 1 obtained 92 on one test, and the results, yep, they were normally distributed. They had a mean of 80 and a standard deviation of 6. Did that person do better than student 2 who got 88 on a different test, where the mean was 78 and the standard deviation was 10? So a little bit of thinking time built in there. So which one was more successful? It's hard to say, isn't it? We need a comparable field or a reference to determine who was more successful, because the means are different. Could that mean the tests had different sorts of questions? Distribution's quite different. So it's not just a matter of someone got a higher score than other. There's a lot of factors there. So that's what we're starting to think about over the next few videos. Okay, so what we need to do is look at what we did last time in the video. We did the normal distribution and its function there. And we're going to move to a standardization, I suppose. And really what we do is we do some transformations of the function so that the mean is 0 and the standard deviation is 1. Now if you sub those two values into this equation, it's pretty easy to see that we get this simpler equation here. Okay, and basically that is the standard normal distribution probability density function. Okay, that's the function that describes that. And it's widely used. So it's got a mean of 0 and a standard deviation of 1. Now to cut a long story short, when we perform transformations between the normal and standard normal distribution, the area is preserved. Okay, and that's what you see on your screen here. We have a normal distribution there, and we have a standard normal distribution based on the same set of data, and the regions are of equal area. So that means it's valid to do what we want to do here. In fact, regardless of the area, the values of the mean and the standard deviation of a normal density function, the area under the curve within a given number of standard deviations from the mean is always the same. So we can see this in these other graphics here. So we can see that these, despite the means being different, have the same area under the curve. We have different distributions here with the same mean. Again, the areas under the curve are preserved, so they're the same. The standardization is possible. So if we do this little example here, this little exercise, if we plot on the same set of axes, and a graphics calculator is very useful here. If we sketch the graph with help from a graphics calculator of the probability density functions of, we start with the standard normal one, so that's mu equals 0 and sigma equals 1. And then we plot a normal distribution with firstly these features here in A, a mean of 1 and a standard deviation of 1. Let's examine what we get. Okay, now the functions for each are there, where we have in the second function especially, we have mu equals 1 and sigma equals 1 subbed in. You get the equations there, and you can, if you use it on your graphics calculator, you can see that really it's just translated 1 unit sideways. Alright, so it's moved to the right, the red one. Okay, so that's this one here refers to the red one. Okay, because its mean is 1. It's the same area, just translated one spot to the right, or to the positive x direction. The second one, we we have a mean of 1 again in the second graph, and we have a different standard deviation of 2 this time. So the data is considerably more spread out. So again, we've got the error is the same, even though you can't see it just by visualizing it. You'd be able to use technology to verify it. You notice that this one here has been dilated by a factor of 1/2 in the y direction. In other words, it's been compressed, okay, or it's been dilated away from the y-axis by a factor of 2, but it's been compressed or dilated vertically by a factor of 1/2. You can see that hopefully there, and then it gets translated to the positive x direction or to the right by 1 unit. More in the next video.